Okay, started. Okay, so we only have one one example left for chapter 2. So last time we talked about how to determine the strain energy and strain energy density, and we noticed that the cross section, the geometry, will change. A material, the ability of the material store, how does the material store energy? So you see different cross section, and they can store more or less strain energy. And also when you considering different loading in different material in the same material, the results cannot be superimposed. Okay, superposition. Okay, you cannot add that because there will be extra term occurred in the formula. So finally, it will be related to the force and displacement. One single load and the displacement are in the same direction. Okay, this questions is that there are two materials, blue material, and connected at point B and with the load P to the downward, okay, to downward direction. And actual rigidity, well, it's just EA, okay, Young's modulus E, and cross area, cross section A. Find the vertical displacement delta B. Okay, so we want to find the displacement of the B point. So we have several solution. We have two solutions, but before the solution, we need to write down the free body diagram because we want to see the internal force of the materials. So we're just going to cut it. So what we do is just we cut it. Okay, we cut it and we have a force downward P, right? And because we cut it, we definitely will have a force because this is actual member, actual bar, right? So we will have a force like this, and they are symmetry. And their angle will be beta, okay? According to the according to the what is it? Properties, yes. And now we are going to draw figures that if you have this type of okay, and this one, right, C, B plan, and B, and that, okay, and this is beta, okay, and actually, I believe you know that this figures is exaggerated, okay, greatly exaggerated, but actually the deltas B, which is what we are going to determine, is actually very, very small, okay? Very small. Very small, okay? Very, very small. However, I just draw it really exaggerated, okay? And we know that the is okay, and suppose these two lines should be the same, and this one is sorry, So this angle is approximately beta, right? Because they're too small. But we know that this is delta BC. Okay, so it's a little bit weird that although you know they are very the length of the bar was changed, delta B and delta BC definitely, but they are really, really small. So because they are very, very small, so we can say, okay, this angle is approximately equal to beta. Okay, so when we have this solution one, when we have this geometry relationship, we have a solution one, delta BC equal to F, the length of BC, divided by EA, okay? And F is what? Let's take a look. F equal to P divided by 2 cosine beta, right? And also AB equal to BC equal to H divided by cosine beta. Okay, according to the geometry shown in the figures. So we have F equal to P divided by 2 cosine beta, and AB and BC equal to H cosine divided by cosine beta. So they are all known value. Now 2 cosine square beta E8. So the delta B will be delta BC divided by cosine beta minus, well, small theta, right? The small theta, but because the delta theta is very, very small, so I'll just reduce that equal to 0, and then it will be pH divided by 2 cosine 3 cubic beta EA. So this is the solution one, okay? Solution one. Solution one. We based on the these figures and the concept of infinitesimal strength, infinitesimally deformation. Okay, so solution one is straightforward. So basically, we finished this problem, but we want to introduce another thing to you by using strain energy, because the loading, because the strain energy stored in the material will equal to the work done by the force, and the force that the work is done by the force times the displacement, right? So basically, the energy is a strain energy. Strain energy stored in the materials. In the material is U. The U is internal energy, strain energy, equal to half F delta BC. And then you have 2 bar, right? You have 2 bar, and then each of them, the strain energy of each bar is half F delta BC. Okay, so you see that delta BC is, sorry, there's one missing, BC. I'm sorry for that. I don't know why it's gone. Delta BC, okay? So delta BC here is the increment, the elongation of that bar, right? Delta BC. So this is the energy stored in the material. 2 times F squared BC divided by 2EA, and which is equal to P squared H divided by 4EA cosine square beta. Okay, this is the energy stored in this system. And we know that this strength energy stored in the material are equal to the work done by the force. So what is that work? The work equal to P delta B divided by 2. So now you are able to using the internal energy, strength energy to determine delta B, and then you see that they are exactly the same. You can obtain exactly the same value of the solution 1. Yeah. So I mean, you can always solve this problem by using this, right? But by using this, you can understand that the work is actually the way you store the strength energy into the material. Okay, so I think this is quite useful problem to show you that actually everything is linked. OK， 能听得懂吗？就是其实你可以直接用前面这个东西算就算出来了哈，就那个 deformation 算出来。但是在右边这个 solution 2其实是一个证明，就是说你的 strength energy 存在你 material 里面，真的是靠你的外力去对它做功。那什么外力怎么做功呢？力乘它的位移嘛，对不对哈？那既然这个位移只有一个方向，力也只有一个方向，表示说你的那个能量都只有一种来源而已。那你只要一除以它的力，就可以得到它的位移了。OK， 所以其实还蛮聪明的一个做法。Okay, so I guess this is all for chapter 2. Congratulations that you've done the chapter 2. This is not easy. And the next part, chapter 3, I believe it will be almost the same as chapter 2. I hope you understand every detail in the chapter 2, and it will make you easier to learn chapter 3. Okay, so now we're going to enter chapter 3. 哎，请说。三次方。Let me take a look. I'm sorry. Did I do it wrong? Which one? This one? This one? 哎，好像是哈。对，是 yes. This is 3. Thank you very much. Yes. Is that okay? Thank you very much. So can you let me know your numbers? 027. Oh, 613. I'm sorry. But the way you pronounce your number is really professional. That's great. That's quite nice. 111-613 027. Okay. 027. That's nice. Good. So this is the chapter 2. I'll finish that. Okay. Great. Chapter 3 is related to torsion. Torsion. Okay. Just like you squeeze your towel. Okay, squeeze your towel, or you the wheels on the car, on the bus, when this actual shaft rotate, and it will make the wheels goes around, and then your car will move forward. Yeah, so this is quite important. Chapter 2 is here now. It's finished. Chapter 3. Chapter 3 is related to torsion. 扭转. Okay, next one. Torsion. Torsion is so what we are going to teach introduce is what is twist, torsion, and we want to talk about the stress-strain relationship when your rod or bar after the torsion. And we want to talk about the relationship between torsion and shear. Okay, I believe you remember that when I talk about the shear, I also introduced indirect shear, and we talk about the twist or torsion relationship. Yeah, and also the relationship between E and G. Remember that I talked about the shear modulus, and we talked about a equation, the relationship between E and G, and I said I will prove that later, and we will prove that in this chapter. And torque and power, horsepower, yes. So you always heard about the car or the engine has how many horsepower is actually the power efficiency or power output of that engine. And torsion is strain energy. So basically you can see the structure is really similar to chapter 2. The structure, the logic is really similar to chapter 2. So now introduction. Definition of the shaft. The shaft is typically something linked to your engine, okay, or motor, okay? So the motor or engine will rotate and make the shaft rotate, and also the wheel will put on the ground. So the before it starting rotate at the equilibrium state, and then the force on the ground will try to stop the torsion due to the motor. Okay, so that's the time we are going to discuss in this chapter. 所以其实今天我们在讲的不是在转哦，我们是在讲转之前的平衡状态哦。OK，就是那个马达在要转之前，就是它要去抵抗那个地板的摩擦力的时候，它在一个平衡状态。然后如果你今天再加一点，它可能就真的在转的时候，它就是动态的东西，就跟我们的材料力学是没有关系的，我们不在我们的考虑范围之内。那所以实际上我们现在讲的还是在 equilibrium 的状态。So all the status of the bar we discussed in this chapter is still in the equilibrium state. So they are stopped. Okay, they are stable. They're not rotating. They just at the equilibrium state. So, well, we are not discussing dynamic rotation. Okay, so let's take a look. So you can imagine that a bar with a force couple. Okay, the force couple, or you can say this is a moment, because the moment is actually the force with a force arm. It's a force arm, right? 力背, okay? And you can imagine that if you have a bar and you have P2, and with the D2, you can have a rotation like this, or we can say torsion. And this one, P1, so you can have a torsion like that, okay? So you can say the T1 is equal to P1 times its D1. The D1 is definitely the force arm, between them. T2 equal to P2 D2, okay? And then it's difficult to always plot such difficult symbol in the bar. So we just simplify our symbol by using double arrow. Okay, the double arrow will tell us if we're using your right hand, we are using our right hand with a thumb along the arrow's direction, and the remaining four fingers represents the torsion direction. Okay, so you see this one, you have that direction. So you see that direction. right? And then if you have a T1 with left hand side, which means that your forefinger rotate like this. So it rotate like that, and F is like this, right? So basically, these two things are equilibrium. We only make this force couple into a simplified torsion symbol. Okay, so now you can see that as really similar to force, but with the two double arrows. Okay, next one. So now we're discussing the fundamental basic example, which called pure torsion. The pure torsion means that the force, the bar only subjected to one single torsion, T here. Okay, so you can imagine that this is actually a wall fixed on the other side, on the left hand side, and the torque performed on the right hand side. And of course, this torsion is kind of reaction force, reaction torsion. Okay, because this is fixed on the force on the wall. So the T here make it a torsion like that. Okay, so it will be like this one. Okay, this torsion direction. Now, we are going to introduce a really important concept called angle of twist. 扭转角, angle of twist. Your unit is radian, okay? And we call this phi, but you notice that we have a x here, which means that it is the function of x. It's a function of the position, okay? So when you think that, when you assume that this is a fixing point, fixed support, a wall fixed on the support, and then you draw a line here. You draw a line, okay? And you draw a point here, point here, point here, okay? And then we said, this is the cross section. This is the cross section belong to this one. Okay, and this is the cross section belong to this one. Okay, and then you can see that the phi here, the x equal to 0. Of course, x equal to 0. But here phi L, because the x become the L direct x equal to L. Okay, phi L. And then I'm going to write down here phi 0 is 0, because you can imagine that they didn't, if you rotate in here, if you rotate here, actually nothing happened here because they are fixed. This section is fixed on the wall, so there's nothing changed. The phi equal to 0. But when you rotate, start from the left hand side to the right hand side, you can imagine that if you rotate here, this circle will start from Q to the Q plot, because you rotate that, right? The point here, Q, because of your torsion, the Q points become Q plot. So you can imagine that Q become Q plot, but in the x equal to 0, it doesn't change at all. Q and Q plot at the same point. So in the middle, it will be Q plot, but with the smaller angle, right? So your 0 and the phi, and you should say phi L, okay? The angle of twist at the distance of L. So again, I will try to emphasize that this one is a function, right? It's a function of x. And the phi L is a scalar, okay? It's a number, it's a value, okay? So don't mix up phi of L and phi L. Phi L is a number, it's a value like 3, like 2, okay? So, and the phi 0 is 0, okay? So I guess you can understand that. Imagine that you have a torsion here. The torsion of the angle of twist will start from smaller one and expand to the bigger one, okay? So the phi here, the cross section area, you will have the phi start from 0 and gradually increased, okay? I believe you understand that, right? Okay, then I'm going to enter the next page. Torsion deformation of the circular bar. Okay, again, the same stuff. But now we are not going to, we're going to focusing on the element of a bar. We just cut it. Okay, cut here, cut here. Previously it's X and L, right? We just cut it, become dx. We are focusing on one element in that, in between that length. We just cut it and we take a look. And because we extend it here, right? But because we are going the material subjected to a pure torsion, so this is easy. So it's here, it's still T torsion, right? Now, this is really interesting. Please be careful. So you can imagine that previously we set this point as the origin, right? But now we are still can also focusing on this one is the origin. We only want to know the decrease of the phi within dx. So here it is a d phi, this is a d phi. So we want to know the phi, change of phi between this element, between dx. So we start from here, A, okay? And the A, B, C, D is the surface element that we can plot a, maybe just a rectangular. Okay, we just plot that before the distortion. We just plot that. We plot a, we're using our pen. We plot a rectangular on the surface. And then after the rotation, torsion, the shape will look like A, B plan, C plan, D, right? So you can imagine that A and D stay the same. The reason is just similar to the previous page. But the B become B plan, C plan becomes C plan. And then if you flatten the surface element, you can imagine that this is A, B, C, D. And this become A, B plan, C plan, D. So the rectangular become a parallel, I mean, I don't know, parallelist, I don't know, the 平行四边形, okay? So you can see that this one, sorry. This pizza shape, okay? 扇形要怎么讲？扇形 pizza shape. I don't know. You know what I mean? Pizza shape is actually this one. Yes, this pizza shape is actually this one, and this is we call this gamma. This gamma is gamma mix. Maybe you will ask why it's called mix. I will let you know later. Okay, we just say this is gamma mix. And this one is defined. I believe you know that because this is angle of twist. We defined that in the previous page, right? So in the cross section, the d phi is open define. After the dx, it open d phi, and we want to add another thing called gamma mix here. The gamma mix is the gamma is the angle, not in the cross section, but in the surface. Okay, careful about this. And we also notice that the pink pizza shape is sharing B and B plane to another pizza shape. Did you see that? Another pizza shape here. Okay. So B and B plane is sharing by two pizza shape. Now, because of the sharing of the same length, so we can using that to correlate them. So the surface element has become a pure shear state, and the angle BAD is that BAD? Oh, BAD is a D, right? D. BAD reduced from the 90-degree become gamma mix. Okay, from 90-degree become smaller gamma mix. The gamma mix equal to BB plot. This one divide by AB. Okay, I know. Maybe this is not a perfect pizza shape. So AB and B plan, AB and AB plan, maybe they have slightly different, but because they are infinitesimal small, so AB approximately equal to AB plan. Okay, so BB plan divided by this one is gamma mix. I believe everyone you know this. And again, BB plan here is RD fine, RD fine. Okay, RD fine. So BB plan become RD fine, and AB is actually DX. So now gamma mix equal to RD phi divided by DX. And then if we so give you this one. Wow, I shouldn't use this. Okay, green one. Okay, BB plum become RD phi, and then we notice that d phi over dx can be simplified as a value or symbol become theta. So the theta here is not an angle, it's the twist rate. It's a rate. Okay, so the unit is not radian. It's not radian. Radian. And it's radian divided by meter. Okay, radian divided by meter, because dx is a length, right? It's a length, unit length. So this is theta is the unit of the theta is not radian. It's radian divided by meter. Okay, so be careful about this. And later we will tell you that why this is mixed, because this is on surface. Okay, later I will tell you why the shear on the surface is the mix. Okay, so in the purest torsion, the theta remains constant, remain unchanged. So theta is equal to phi divided by L. So which means that they has equal rate of displacement. So you can see a line, linear changed. Okay, the phi will be linear changed along the x. So gamma makes equal to r theta, r phi divided by L. Okay, that's it. Oh, sorry, I should give more L. This is L. Okay, because the phi L will be the longest, the greatest phi L divided by L. You can see the theta, which is twist rate. OK， 好，这边不知道大家听得懂吗？就是说我们用表面的画一个方块，然后呢看这个 torsion 加载下去，它会变成什么样子？就发现就变成一个平行四边形。平行四边形就表示说它是一个 strain 咯，shear strain 对不对哈？也就是这个 gamma max 其实是 shear strain 的值。那 gamma 为什么要写 max 呢？因为它在表面。等一下我就会告诉大家，其实表面的 gamma 是最大的，往内就是钻下去的话，它会没有那么大。等一下会仔细跟大家介绍。那 gamma max 的话呢，它其实就是用这个扇形算出来的 b plan divided by ab。那 b plan 又可以用跟 define 扯上关系。那 define 跟 dx 其实可以写成一个扭旋率哦，扭旋率哦，那就是它的扭转角的改变的程度啦，哈，的速率这种感觉，往前多少它改变多少这种感觉，所以它的单位不会是 radian， 它是单位除以长度哦。然后在 pure torsion 的时候，当然就是固定的扭旋率嘛，所以你只要把最大的 phi l 除以它的长度，就是它的固定的那个定值的扭旋率，然后你就可以得到 gamma max equal to this one。OK， 好。我相信大家听得懂了。Next page, I will going to tell you why the gamma mix occurred in the surface, at the surface. Okay, so now we are talking about the shear stress inside the bar, not in the not in the surface. The surface must be the tau mix. So you can imagine that when you have a bar cross section, this is cross section. Okay, you have a cross section, and when you rotate it, apply your torsion. You're usually using your hand, grab the torsion, grab the bar, and then do the twist, right? So you can imagine that your torsions applied like this, and then you can imagine that actually the center never move, right? It never move. Just rotate it, and the rotation must be has the surface with the greatest distortion, and then in the center it never move. The center never move, right? So if you can accept this, you can think that actually this is tau mix. Tau mix at the surface, and zero tau equal to 0 at the center. So you start from here, tau max, and then you need to gradually decrease to the center and become 0. So it must has a triangle shape. So your tau maxima at the top, and then gradually decrease into the center. Okay, and then you can notice that actually you can do that everything again, but previously your gamma max equal to r theta. Now you can imagine that your r is not r now, because you're going to dig into the spar. So now your surface become low. The low is smaller than your r. The low here is smaller than your R. Okay, so this is the low mix become R. Okay, so you can imagine that the theta here, the theta equal to gamma mix divided by R. Okay. Oh, this is, I should write it down, make it more. Okay, I shouldn't write it. This is gamma, this is R, and this is R. Okay. So this low is less than R. So your gamma not mix. This is not mix, okay? Gamma equal to low theta. The low is the inner radius, okay? Low theta, and your your theta equal to gamma divided by R. So you can imagine that your gamma not mix. The gamma is actually the ratio between the low and the R. Okay, so gamma, not mix, gamma is equal to the gamma mix times a factor, a ratio. And this ratio is actually the ratio low to the R. 好了，那讲基本上就是其实啊哈，你的伽马哦，你的伽马就是你的叫什么检应变啊，这个检应变其实是跟你的 gamma mix 是成线性关系的，越来越小，越来越小，到就是跟你的线性关系跑到它的 center 中心是为零啊。那所以其实基本上这个 law 就是你在哪一个位置，这个就是你在那个 bar 的内部的哪一个位置 ，law 的最大值就是 r， 那最小值当然就是零嘛，对不对？好 ，low 啊，low 等于零。那所以你的 low 不管在哪里的时候，其实就是 low 除以 r 这个 ratio 乘上它的 gamma mix 就会是你当下的 gamma。OK， so it's a kind of it's a ratio is a ratio yeah of the radius. Okay, so it's not that difficult. Okay, and hollow tube, you can imagine that this one empty inside, and then you cannot have the shear force, but it's still the same. Okay, the ratio between the ratio of the gamma mix and gamma are still the same. Okay, and yeah, that's it. So the gamma mix equal to this one is the same, but the gamma minima will be R1 over R2. Okay, it's still the same, just a ratio between them. So yeah, that's it. Hollow tube and bar, they are all similar with the gamma mix at the surface and with the linear relationship and toward the center. Next is a Hooke's law. The Hooke's law, shear stress on the surface. Of course, tau max is on surface, right? Tau max equal to G gamma max. And gamma max equal to R theta, no problem. Okay, we introduced in the previous few pages. And of course, if we are talking about inside the bar, so the tau is no longer tau max, no max, right? Tau equal to G gamma, no problem, right? The gamma equal to log theta. You see, log and R, they are really, so log divided by R is the ratio times the tau max, no problem. That's it. And now we are going to link these things to the material that you can see in the real life. So you know that shear stress is mutually perpendicular planes will coexist, right? They will occurred in pairs. So remember that if you have a tau like this, you definitely will have another opposite side in opposite direction. And because this is rotation like that, you will have rotation like this one. Yeah, that's it. So you will see that it will happen simultaneously, 4 pairs. Okay, sorry, 2 pairs, 2 pairs. So now, if you have a rotation, if you have a stress element, we draw here. If we draw here, okay? And then if we know that the shear stress, the shear stress is here, it definitely tell you it will have another pair in that surface, right? And you will notice that this one is gradually decreased. And so this one is also gradually decreased. Okay? Right? So you will see that it actually, the element in the middle, we actually caused a resultant force in that direction. So you can imagine that actually this one, if you draw the element with 45 degree, you will have element like this. And you will notice that if you do a rotation to the bar, the cracks will along 45 degree. Okay, so you can notice that when you do the towel, you do the twist, you do that, you destroy that, and you spread it out, you'll find the cross crack. Okay, that's it. So I will let you, if you have any questions, just let me know, and I will see you after 10 minutes. Thank you.说
哎，这个如果切在这里的话，那我还会需要考虑 Q 跟 P 吗？
就看你要留在哪，你要留哪一个方向，你要留这边就不用考虑。但是你以为你就没有考虑到？没有，因为你的 RA 会跟你的 Q 跟 P 有关系啊，所以你不管留哪边，你都会考虑到 QP。只是你在画的时候，你留左边的时候，你就遮住了，你就只要考虑 RA 就好，还有它这个 N1 就可以了。
所以要留哪边是
随便
自己知道的，
对，随便，自己知道就好，没有错，没有错。
所以是我切的随便切，
你随便切都可以。
他们的力都是一样。
对，就是那应该这样讲，你如果因为中间已经变化，就是这个过了这点就变化了，所以说你切这边都会是一样的。然后你切这边跟这边，当然会跟这边不一样哦。你切这边之后都会是一样的。
可是我
第一段跟第二段，
我切这边的时候，
对，
我还是需要，就是我会需要画 RA，还是我已经
你要看你要留哪边。你如果留这边，你就要画 RA，你就不用看 R，就不看 P。但如果你留那边的话，你就只要考虑 P 就好。
我画这边，然后我如果只有这样，
对，
我就是没有 Q 跟，
对，就没有 Q 跟 P。
那为什么我不用考虑 Q 跟？
因为 Q 跟 P 它的合力会在 RA 那边显现，所以不用担心。
是因为我没有画到它开始失 Q 的地方。
不是，因为你的 RA 会跟 Q 跟 P 有关。所以你说你这样子留在这边，我不用考虑 Q 跟 P 吗？没有，你有考虑，只是它的效用已经被 RA 所取代了。对。
好， 但是如果我要算那个 delta 的话，我是要再补一个
N1，对，因为它是在内部的力。对，
好，
哎，
好，
加油，很棒。问我问题吗？对，好。我印象中啊，就是它是这样推过去的嘛，对，所以说它会有一部分是，让我想想看哦，就它会阻挡它的力，大概就是一个圈圈再把这个扣掉，一个圈圈再把这个地方扣掉，因为它是空的。哦，我们是想问那个力要怎么算？力要怎么算？力要怎么看？好，怎么说？你怎么？我的理解是因为它4个片都把这个板子压在这个面上，所以它风吹的时候不会动。就它风吹的时候，它可以做一个力矩。好像只有2个会用有力哦，对，只有这2个哦。一是问，好像只有两个有作用，因为没有啊，问那个就是不要那么倒。对啊，所以说只有这2个会有用，这2个就没事，没作用，因为他们在上面。看一下哦。对，我想要知道就是说，这个是从上面看下去，对不对？对。好，那所以说你看啊，他如果把这个东西放在这里，就把它合在一起，然后这4颗都放在上面的话，那它被往这边推，也就是说这个东西会翘起来，这个板凳会翘起来。那翘起来的时候，这个东西会被他们2个挡住，他们2个会往下，所以它其实根本没有挡住它。这2个人没有挡住它，因为它是这个板面是往下的，所以他们2个没有被挡住，也停在上面。这2颗是在板的上面的，等于是说这样，更没有感觉。但是它这样，它就挡住了。这样听得懂吗？这个就是下面的这2个在挡它，对。然后它的 stress 代表它的 area 是谁呢？就是这个圆圈减掉这一条缝，这个圆圈减掉这条缝，对。那它算转动的时候不是这样算，转动的时候不是这样算什么意思？就是刚刚讲那个好像是 B 小题。哦，是吗？因为大家都，因为我只是在靠我以前大家问我的记忆词，我的第四个好像是 B 小。好，那 C 小题比较有一个问题是 find the average。washer，那就是我刚刚讲的啊，就是2颗啊，2颗，因为你的力过去以后，就会造成这个板子要往上推，它力将冲上去，就有那2颗的截面去挡下来，所以 average bearing stress 就是那2个面积挡下来的 stress。那个，它就是直接除以2的意思。对，对，除以2，对，对。然后怎么样得到这个力呢？就是它跟它这边的力矩跟的力平等。就是那如果这样子看，那这2颗的力矩的长度要看谁，力臂要看谁？就这2颗，就是h。如果你拿这一点来当做是它的转动的轴心的话，h，然后这个就是 L。那我刚刚算的话，
到这样子就算了。
嗯，
这里变成如果这两个例子一样，就这两个贡献不一样，因为到我们
对，共同因素。
12放在这里去，
对，
WY 这个，那这样子跟答案差了2倍。
真的吗？差2倍。决定，
肯定就是差2倍，
是吗？我不知道解答是多少，但是我记得我是这样算。那有时候解答会错，对，有时候解答会错，所以我建议大家就是讨论一下，然后如果大家就觉得解答是错的话，那就不一定，就是不要影响它。哦，对对对，OK。
在讲科技的时候，你是教到那个西格玛还是某些这 K 那种 K 的那个东西。就你会上面写那个完整的课定律是
我们一跟七就是 share，对，但是
我要算他们的就是
我没有讲到 CIJ 起来，
就是你们讲的，就你有讲那个要什么就是。没有那个学模没有收，这个可能就是纯拉伸跟创新。
对，
但是完整的这个电色其实是外面的，
但是我有教 sigma 2
是什么？对，
我教这个
因为我是在初中那个就是那种的。如果这些
是要用这个，
对我才不懂。
他修完这个上面，他可以升起来，然后。
这往下，如果这个是叠在这样，这个往下会卡到
缺陷。
就是它这个比这个大，但是我这往下，这边不是会跳起来？因为这边跳起来的话，这边不就找不到？就是它下半圆，半港刀的板子。
你是说它下面还有？
对啊，就是没有，不是，就是这样子。它这样子不都会卡到？
你是在这里？
对啊，对啊。
那个很刚，
这个我听到的，
你讨论的很现实。
对，
层面，
它不会卡刀。
这边。是 X 对，这个很让人去过。
喂，喂，好，so I just received many questions from the practicing examples, and I will suggest that you can email to the teaching assistant first, and if he cannot answer you, I will write the complete solution for you. Okay, so that will be easier for me. Okay, if he cannot do that, if he cannot help you to solve your problem, I will be there. Okay, right. So let's continue our lecture. And然后我觉得啊，就是现在这种年纪，时间过得就觉得好快，就是像刚刚10分钟下课，我还没有离开就已经打钟了，这样我觉得哇。但是我以前小时候，我印象很深刻，我在国中的时候，一下课也是10分钟，但是我们一打钟完，我们就从3楼的教室还是5楼的教室忘记了，跑到操场去打球，然后在下课钟结束以后就跑回来，那根本就没有，大概只打了5分钟吧。可是当下就会觉得我们就做了一件事情这样。那现在我去上个厕所就10分钟结束了。哦，我只能觉得说，当时真的是年轻的时候的时间真的是过得很慢，然后老的时间过得很快。这让我有一个理论，你知道吗？就是反应跟你的寿命是成正比的，是成反比的，sorry，是成反比的。就例如说，我就觉得，你看乌龟为什么可以活得很长寿？因为它就动得很慢嘛。但是如果是鸟啊、狗啊，你看狗跟猫，它的速度就很快，你看它的头的动作就是这样，是，对不对哈？它就只有我们人的寿命的几分之几。所以我就觉得说，好像是不是都有这样子的？那像我说老了嘛，老了你的那个反应就变慢，所以你就会觉得时间过很快。那你最常听到一句话就是，老师或是老师，好，好了，老师说，那我简短的讲几句话就好，然后就给他讲了1个小时这样，因为他真的觉得他简短的讲了几句话啊，这是他真的这样觉得，只是他的反应的状态跟你的状态不一样，这样，他真的觉得他讲5分钟而已啊，我讲5分钟就好，结果他真的解决他讲5分钟，但实际上对你来讲是真正的时间大概已经过了1个小时。对，大概是这样。Okay, next. So now, oh, by the way, this one is really interesting that if you try to do your torsion, in the bar or in the towel, maybe you can find why the cracks typically in 45 degree. Okay, and you can see the building, okay, maybe you can see the wall after the earthquake, it has a cracks. That's because of this one, right? And you see that yeah, you see, if the rod made of a material with weak tensile strength, so it's difficult for it. The material is not strong enough to against the tensile. You will have 45-degree cracks, and you see that concrete is the material that weak at tensile. Okay, concrete. Okay, so that's the reason why you see that in cross cracks， 就是抗拉比较弱的材料，就会在45度角的时候你看它45度就被拉了嘛，对不对哈？它就被拉开了这样子。那水泥就是一个很难被拉的，就是很难被拉长的材料，它很容易，它压很强，但拉很弱。 所以就常常看到那些建筑物啊，都是有就是45度角的 crack，就是大概是这样。Okay, next, let's talk about the torsion formula. What is torsion formula? When we see the chapter 2, we have sigma equal to P divided by A, right? This is the equation that we have, right? Now, how about tau equal to T? Well, I should say, what's the relationship between the shear stress and the applied torsion? Okay, so this relationship is really similar. Sigma equal to P divided by A, but how about tau related to torsion? Okay, so this is called torsion formula. So now we have the area at the radial distance law, okay, is dA. So now we will have a dA dA, okay, this is dA. And it at the dA, it has a tau at the cross-section area. Okay, so you can imagine that the shear force, shear stress at the act on the dA and distant to the center is low. Okay, and that shear force at that area is tau dA, of course, right? Shear stress times the area dA is shear force. So this is shear force, and the shear force, the torque done by that shear force is shear force times its force arm, low, right? So tau times dA is a shear force. And the law here is the arm, right? So the small torsion is equal to the detorsion, dt equal to shear force times arm, shear arm at the small area. Okay, and then the tau max, we will just transfer the tau here into tau max. What's the relationship between tau and tau max? Because we know that the tau equal to log r tau max, right? The ratio, right? So we just replace the tau, become tau max divided by r times log, and log times log becomes squared. Okay, so dt equal to this one. I guess there's no problem for you all. So now this is dt, small area torsion. How about the entire area? We just do the area integration. So the total torsion equal to the area integration dt. Okay, so doing that, and then we found that, wow, this is ugly. What is ugly? Log squared dA area integration. So this one is ugly. So we try to cover it, become IP. Okay, so this is ugly form. I just make it IP. Right, the IP, the IP here, P means polar. Okay, 极坐标的意思。IP, what is I? I is called moment of inertia, 惯性矩，惯性矩。Polar moment of inertia, 极惯性矩。IP, the definition of IP is Rho squared with the integration, area integration. Okay, so what will it be? Okay, let's take a look. It's a little bit difficult, but don't worry about that. I will show you step by step. So rho squared dA. Okay, so dA. This is dA. Okay, and because this is in polar coordinate, so yeah. Okay, and here is the law, and this is law, and this is the theta, right? And this length is log the theta. Okay, so your dA, your dA, dA, your dA equal to your dA equal to d log times log d theta, right? So this is your dA. Your dA needs to be do the integration, area integration. So 0 to pi 0 r log square. Okay, log square dA. We just write down dA here. dA become d log d theta, and then you can do the integration based on what you learned in your first grade, first year. 0 to pi 1/4 r4 d theta and equal to pi r4 powered by 4. Okay, so that's it. So your IP is the moment of inertia, the polar direction. If the cross section is a circle, your IP become pi r to 4 divided by 2. Okay? And oh, and also the moment of inertia can be look up in the appendix D in your textbook. Okay, appendix D, appendix D. So the appendix D has many moment of inertia for different shape of the cross section. Okay, it should be it could be rectangular, square, triangle, circle. Okay, many possibility. So the IP, you can see the appendix appendix D with the IP equal to pi r4 divided by 2, and also they may written down as pi d4 divided by 32 using diameter. Okay. So if you can accept that, our tau max equal to TR divided by IP. Tau max, you change it. Tau max equal to TR over IP, or tau max equal to 16T. So you can just replace that as the R become T. And then shear stress at the distant load from the axis, tau equal to T load divided by IT. So R become low, everything is okay. So now we know that the relationship between tau and T, so tau and T, so torsion formula. That's it. So we obtain exactly the same relationship about sigma and P and the tau and T. So you can see that, oh, the tau and T is actually the A is really similar to IP over R. OK， 这样应该听得懂吧？哈，就是我们把小单位底 A 的 shear force 乘上它的力倍，就是那个小单位的 area 的 torsion。那我把它积分起来，就会是全部的 torsion。所以全部的 torsion 会等于它的积分面积分。结果发现哇，这后面这个写的好丑啊 ，low 平方啊，好丑啊。low 平方的面积分好难写，不过没关系，底 A 还蛮简单的哈，就把它写出来以后，就可以积分出 IP 等于派 r 4次方除以2。这个东西是对圆截面算出来的哦。如果是方截面，哎，那就不能这样子带了哦，要小心。那方截面、圆截面都其实古早的数学家都帮你算好了 ，Appendix D 你就可以去查了，它会写的派 D 4次方啊，除以32。然后我们的 tau max 就等于 TR 除以 IP。那如果是 tau 不是 max 的话，那就是它在哪里的半径就是在哪里就对了。那这个就是它的 tau 跟 T 之间的关系，就 torsion formula。Okay, now I am going to give you more information about moment of inertia. Moment of inertia is actually how difficult the shape rotate about certain axis. Okay, so if you have more larger, greater moment of inertia, which means that that shape is more difficult to rotate about that axis. For example, well, I will give you an example later. Okay, so I just give you a definition first. So Ix equal to this one. What does that mean? Which means that Ix is the difficulty of the material of the cross section, also cross section, rotate about x axis. So how difficult of that area rotate about the x-axis? Okay, so rotate about x-axis 对 x 轴旋转的难度啦，的难度越大就越难转。Okay, I will give you a really solid example later. You will understand that. Don't worry about that. Okay, so you see that because if we want to rotate this area, this area rotate about x, what is the force on? Y, right? The force on the distance between the dA to the axis, y. So this is why you have y squared dA. Okay, so now if you have a Iy means that the material, the cross section rotate about y-axis. Okay, so this area rotate about y-axis. How difficult it will be Iy. Okay, so polar IP is low square dA, and which is Ix plus Iy. Why? You see that Ix and Iy is y squared x squared, y squared x squared. Somewhere not together become law squared. 毕氏定理啊，对不对？ So Ix plus Iy equal to law square. You see that? Do you understand what I'm saying? Law square equal to x squared plus y squared, right? So IP equal to Ix plus Iy. So this is the extra information. So I hope you can sort of understand what is moment of inertia. But now I will give you a proper example, I believe you understand that. Now, if you have a material shape cross section as square, okay, and what is the IX, IY, and IP? Although here JC, it was writing down JC, but actually it should be IP lah. Well, in different textbooks, they will have different symbol. Don't worry about that. But if you or just open your book, you will find out that JC or IX and IY and IX plan, IY plan. Okay, you see, this is a typical formulation you check up in your appendix D. This is that figure. So I will let you know how to see that figure, how to understand this. So now, if you have a square here, and here is X plan, which means that the X axis going through the center, okay, the centroid, and Y plan means that they go to Y plan center, right? And the X is on that boundary, on that rectangular boundary. Y is on that boundary. Okay, so let's see which axis is easier for you to rotate. So you see that the IX, if you rotate about X, if you rotate about X, it's called 1/3 BH3. And if you rotate X plan is 1/12 BH3. So which one is bigger? This one, right? This one is bigger, right? This one is smaller. So that I would give you a hint. So this is the cross section, okay? Rectangular, right? And now I'm going to rotate about an axis. So now X-axis, I want it to rotate about my hand, my arm. So it's rotate. Okay, don't you think it's a little bit difficult? A little bit difficult, right? Now I'm going to rotate X1 along the center. Okay, I want to rotate about this. See that? Is that easy? Yeah, so that's the reason why 1/12. Okay, believe you understand now. Good iPad. That's it. So that's it. Angle of twist, hook law, right? Hook law, tau equal to T law divided by IP. That's what we learned. And so the theta equal to T over GIP. Yeah, that's just moving around. And in pure rotation, pure torsion, the theta is constant. So theta equal to phi divided by L. And if we substitute this theta here, and then we can obtain phi equal to TL divided by GIP. So the phi here is equal to TL divided by GIP. Phi is the angle of twist. So the result of the torsion. Don't you think this formulation really similar to what you learned before in chapter 2? Delta equal to PL divided by EA. Don't you think that looks really similar? P about T, and L, E, and G, A, and IP. So yeah, the delta is low. So the result of the actual force, the result of the torsion. So they're really similar, right? So we can compare the actual stiffness K equal to EA divided by L, the K torsion stiffness GIP divided by L. So A really similar, related to IP. Okay. So I believe all the logic is really similar to chapter 2. So if you understand every detail in chapter 2, you will be fine in chapter 3. Okay, next one is circular bar, circular tubes. 休息一下好了。我不跟大家讲，我最近眼皮一直跳，没有，我眼皮一直跳，已经跳了大概2周了，而且他那个跳不是我感觉，我是看得到镜子，然后那边这样噔，我担心我会不会中风或什么之类的。有没有大家有没有这样感觉过？有没有这样经历过这样的事情啊？眼皮一直跳。我现在不是在讲那种就是那种预兆或者发生什么事那种算命的，不是，我是在讲身体，就是后来怎么解决啊？请问你后来怎么解决？还就自然好了？可他真的很久2个礼拜了，跳得很严重怎么办？我好担心哦。有没有其他同学可以告诉我一下我该怎么做的？神经外科，神经外科。好，如果我今天1个月后还是这样的话，我就去看。他就等，然后一开始是这里，然后前几天变成这里，就2个一起，奇怪哦，真是的，人老了就会有一堆有的没的出现这样。OK， right, circle tubes, circular tube. So this is the formula we just introduced, right? Tau T law divided by IP, phi T law over GIP. So normal tube looks like this, right? And your T is actually the thickness of the wall, right? So it should be R2 minus R1. And suppose this is tau max. And of course, it will has a tau minima because it's not reached to the 0, right? So it must be tau minima and then it finished. Right. So this is really interesting that IP is the properties of the cross-section area, right? So your cross-section area, the middle part become empty, right? So you just need to divide minus R1 4 to 4 power by 4. Okay, so that's it. Okay, everything will be the same, but the area cross-section area changed, so your IP changed. Straightforward, right? Next, thin wall tube, which means that T is really small. So if T is really, really small, which means that you're allowed to neglect some terms in your formula. So IP is approximately equal to 2 pi r cubed T. Why? Because if you have pi divided by 2 R2 4 minus R2 minus T4. Okay, because your R1 is actually R2 minus T. Okay, and then you can expand it and neglecting T4 and T squared turned, and you will obtain this result. Okay, if you expand that, and neglecting t 2 power by 4 and t squared because t is really small, right? So t squared and t power by 4 are really, really small, extremely small, negligible. Okay, so you will get this one. And then you will notice that when you talk about the efficiency, when you are a boss, when you are a company, you want to save the material cost, typically using tube rather than solid bar. Because you can notice that the tau here is actually quite small here. The values here really, really small. So if you want to resist that small tau and you feel all the material inside, that's really not efficient. Okay, so if you want to save the material and saving weight of the system, you typically suggest it by using circular tube. Okay, it's easier, it's more efficient, cheaper. Okay, right. So that's it. 讲到这个，昨天有一点点时间看了一下《三体》（Three Body Problems）， 没什么感想，就看到一半了。但是，大家知道我是牛津毕业的吗？我是牛津毕业的。那里面的那个人，主角发生的地方就是牛津，然后它里面有非常多的东西是真的是在牛津。然后就看就哇，好有感觉哦。就例如说，有一个博士在里面的博士，他的毕业照在里面，他穿的博士服就是我这个博士服哦。你可以仔细看，是红色跟蓝色，就是跟国旗的颜色是，我们跟台湾的国旗颜色是一样的，红色跟蓝色。所以看到那个照片，我就知道哦，这个人是牛津毕业的，大概是这样，哎，真的是。然后就里面在博士，他就是牛津博士。然后他那边的那个什么那什么加速器的那个场景，然后我不知道是不是真的啦，但是牛津大学旁边真的有一个就是同步辐射中心，也就是真的要有加速的那个，就同步辐射中心，但是在牛津的啦，它叫做 Diamond Light Source， 它的名字叫 Diamond Light Source， 我真的有去那边做过实验这样。但我不觉得它里面有那么帅气的内装啦，就它有一个很像钢铁人的那个亮灯在里面，我觉得应该没有了哈。那当然就是他是在讲这件事情，然后他有在拍那个校园，那是真的，然后就哇好漂亮，就是以前我真的可以去那边，然后进去一般人是要付费的，那我只要凭学生证我就可以进去了，这样。很开心，那所以常常就是用这一招去带朋友进去看这样子，对，那就可以认识很多人，对，好，那我觉得我还运气蛮好的，就是我念的学校都有拍一些电影，都常在电影里面出现，比如说我之前不是讲我是师大附中吗？师大附中当然很老了，有一个很老的片叫《蓝色大门》，就是桂纶镁跟那个叫谁啊，陈柏霖，对，那时候我就觉得哇，我上的高中就是有拍这个片这样，然后后来我上了牛津以后，也会有很多牛津的片这样子，哎，蛮有趣的。那里面常常看到就是说他在骑的地方，就是骑脚踏车，我知道他在哪里，然后他在拍这样一转弯，然后就到了某个地方，当然说，哎，不对，因为转弯还不是这样，这样大概是这样，大概是这样。好，没了，讲完了。好，just talk about some movies are related to my graduated universities and schools. Yes, I'm quite proud of my schools, my universities. Yes. Okay, go. Limitation. The equation derived above, they are only applied for circular cross-section. Circular cross-section, because you saw law R IP, they are all focusing on applied for circular cross section. Okay, and linearly elastic Hooke's law. Okay, Hooke's law, and you can notice that there are many corresponding relationships between torsion formula and actual force formula. I believe you agree with that. And notice that the torsion formula is only for round rods, bars, circular cross section, because we are all using based on the assumption of the cross section was circle, right? If it is square, no, you cannot apply that. Okay, be careful. So now let's take a look how the tube, hollow tube, will save the materials or the cost. Okay, so given the torsion is 1200 n dot m, allowable of the material is tau allow is 40 megapascal, and allowable rate of twist theta equal to 0.0131 radian divided by m. So which means that there are two limitations. The first one is tau allow. The other is rate of twist rate of allowable rate of twist. And G equal to this one, and please find the D0 and D2 if the T equal to D2 over 10. And we want to see the ratio of the diameter of 1 and 2 and the weight about around 1 and 2. Okay, so the third problem is actually tell you how efficient of the tube, how much you can save. So solid shift and easy, tau allow equal to TR IP, okay, T D0 over 2 pi D0 4 divided by 32, which is 16T pi D0 3. So 40 megapascal equal to 16 times 1200 I D03. So your D0 equal to 53.5 millimeter. Okay, so if the diameter less than 53.5 millimeter, it will has shear fraction, shearing fraction. Theta equal to T GIP equal to T divided by G pi D0 4 divided by 32. So it will be 0.0131 equal to 1200 divided by 78 times 10 to 9 gigapart, right? And pi D04 divided by 32. And your D0 equal to 58.8 millimeter. Okay, now, which one we should choose? Which one we should choose? If the 58.8 millimeter, the D0 is less than 58.8 millimeter, it will has twist fracture, because the rotation is too big, the material just fracture. So which one we will choose? Bigger one. Good, good. Very good. So you need to choose the bigger one. Choose the bigger one. Okay, your number is 111. 110, sorry. 110. 613 29. It's 39. Good. Okay. Choose the bigger one. Ta-da. Right. How about hollow one? Hollow. Good. D1 equal to D2 minus 2, 0.1 D2. Don't forget the 2, right? If T equal to D2 divided by 10, okay? So D1 need to 0.8 D2. Okay, so the IP here is pi 32 D2 4 minus D1 4 equal to pi 32 0.5904 D2 4. Okay. So 0.058 D24. Okay, so IP is here. So again, tau allowable equal to T D2 divided by 2, 0.058 D24. So D2 equal to 63.7 millimeter. Okay, and theta allow equal to TGIP 1200.78 times 10 to 9 times 0.058. Uh-oh. D24. So the D2 equal to 67.1 millimeter. Again, we will choose the bigger one. So yeah, of course, because there has less material. So you need to make it bigger, right? Less material, you make it bigger. So 67.1 is greater than 58. Yeah, of course. But we cannot just see the diameter. We need to actually calculate the ratio and the weight. The third problem. D2 over D0 equal to 67.1 divided by 58.8 equal to 1.14. So the diameter is 1.14 greater than the original design. How about W? W hollow and W weight. A solid. Okay, so the area H divided by AS and times L times, well, density. how can I say that? Density. Eta. Okay, and they just cancel. And the answer will be 0.47. Wow. So although your diameter greater than 1.14 times, but you save more than 50% of the materials, and it will be cheaper as well. 0.47. Wow. Okay, so now you know how it saves the money and the weight of the material. Okay, so that's it. I guess it's all for today. If you have any questions, just let me know, and I will see you tomorrow.好，说。
这也是有接触的，等于说它往前的时候，它还没有任何停止，它还是会撞到这两个，所以这两个应该很没有问题。
那就要看你要算哪一个 bearing stress，有往前的 bearing stress 跟这个板子搬的 bearing stress，
对，
那就要看哪一个，你要算哪一个。你说的是对，所以说，
应该是比较这个，
应该有就是 y 方向跟 x 方向的，对，所以你要看哪一个，所以它要算什么？Find the average tension between the upper base plate and washer fold.
跟是，这边就是
Due to the wind force, assume the initial fold retention is 0. 哦，对啊，所以说它就只有往上挡的力啊，因为它往前的话，它根本不会挡住它，它只有往上，它没有往前，因为它这边是空的。它如果真的要走的话，它就可以沿着要走掉了。对，所以就只有往上。
但请问它这个也有往下的嘛？对吗？
这个就有往前跟往下。
对，就是有，
哎，不对，不好意思，这个就只有往前的了，它没有往下，因为它在上面，它往下不就是跟普通的汤，所以它其实分得很开。
但还是只有这两个有往下的，因为它完全反攻就这两个有往下，
这两个会往它往上就把它挡住，对，
要一个往下。
对，这两个是用往下把它挡住的，然后它往前的话，也只有这两个人去挡住前，因为这两个旁边这边是有空的，它不会它分得很开，应该是题目的贴心之处。
不要把